Hello everyone, I'm Saish Manohar. Here to present my tech talk presentation for the course Design and Analysis of Algorithm. The topic I've selected for my tech talk presentation is merge sort algorithm. Let's begin. So let's get on with the introduction to merge sort. Merge sort is a popular sorting algorithm known for its efficiency and stability. It follows the divide and conquer strategy, dividing the array into smaller subarrays until they are sorted. The sorted subarrays are then merged back together to produce the final sorted array. Here is a basic example, a diagram where you can basically see the merge sort algorithm being executed. So here is an array which consists of the elements 38, 27, 43, and 10. So it uses divide and conquer strategy, to basically divide the main array into smaller subarrays. So you can see here 38, 27 divided and 43 and 10 are divided into two subarrays. Then further, they're divided into smaller subarrays, which have their individual elements now. It's a 38, 27, 43, and 10. So accordingly, they are merged together in the order the user wants. So here 27, 38 are merged and 10 and 43. At last, the whole small subarrays are merged into a total main subarray, main array, which gives the output, the sorted array. So let's talk about the divide and conquer strategy. Merge sort divides the array into halves until each subarray contains one element. The division process is recursive, creating smaller subproblems that are easier to solve. The divide and conquer strategy helps achieve a time complexity of big O of log n log n. So here is a basic example, like not example, I would say a relation of merge sort algorithm. So the problem is given in a form of data sets. It's divided into subproblems. The subproblem conquer strategy is applied. Then the solution of the subproblem is obtained. Then the combine strategy comes into picture. Then the solution of subproblem it's combined the solution of the problem, main problem. Sorting the subarrays. After dividing the array, merge sort sorts the individual subarrays. Sorting is typically done by comparing elements and rearranging them in correct order. The sorted subarrays are then ready to be merged. Merging process. The merging process combines the sorted subarrays back together. It compares the elements from each subarray and places them in the correct order in the final sorted array. Merging is a crucial step in merge sort to ensure the final array is sorted. So here is an GIF illustration of how a merge sort algorithm works. So basically the main array is divided into many subarrays like this, and then it's sorted and it's then combined back to the main array. So let's talk about the time complexity of merge sort algorithm. Time complexity analysis. Merge sort has the time complexity of big O of n log n in the worst, best, and average cases. The efficiency makes merge sort one of the fastest sorting algorithms for large data sets. The divide and conquer approach contributes to the logarithmic factor in the time complexity. Stability of merge sort. Merge sort is a stable sorting algorithm, meaning it preserves the relative order of equal elements. Stability is essential where the original order of the equal elements matters. The merging step in merge sort ensures stability by maintaining the order of equal elements. The need for extra space. Merge sort slightly requires additional space to store the temporary subarrays during the sorting process. The extra space needed is proportional to the size of the input array. Despite the space complexity, merge sort's stable and efficient nature makes it a preferred choice in many applications. Recursive nature of merge sort. Merge sort's recursive approach simplifies the sorting process by breaking it down into smaller subproblems. Recursive allows merge sort to handle large data sets efficiently. Each recursive call works on smaller subset of the array until the base case is reached. Comparison with other sorting algorithms. Merge sort outperforms other sorting algorithms like bubble sort, selection sort in terms of time complexity. It's particularly efficient for large datasets where big O of n log n time complexity shines. While it requires extra space, merge sort stability and speed makes it a popular choice in various applications. So here's an illustration diagram which depicts how merge sort algorithm stacks up. So time complexity is big of n log n, space complexity is out of place, stability nature is stable, it's internal or external, it's external, it's recursive or non-recursive, it's recursive in nature. Is it a comparison sort? Yes, it's a comparison sort. So let's discuss the advantages of merge sort. Merge sort's stable nature ensures that equal elements retain their original order after sorting. It has a consistent big O of n log n time complexity for all cases, making it reliable for various input sizes. Merge sort's divide and conquer strategy enables efficient sorting of large datasets. Here are more advantages. It can be applied to files of any size. Reading of the input during the run creation step is sequential. If heap sort is used for the in-memory part of the merge, its operation can be overlapped. Here are the disadvantages of merge sort. Merge sort's main drawback is the additional data space required for storing temporary subarrays. The space complexity can be limiting factor when dealing with memory constrained environments. While merge sort is efficient for large datasets, it may not be the best choice for small arrays due to overhead. Disadvantages: it requires extra space. Merge sort requires more space than other sorts. Merge sort is less efficient than other sorts. Real-world applications. Merge sort is commonly used in external sorting scenarios where data is too large to fit in the memory. It is utilized in database systems for sorting large datasets efficiently. Merge sort stability and predictable time complexity makes it suitable for various applications in computer science and beyond. Visualization of merge sort. Visual representations of merge sort showcase how the algorithm divides, sorts, and merges the array. Watching the step-by-step process can help understand how merge sort works internally. Various online tools and resources offer interactive visualizations of merge sort for educational purposes. Implementing merge sort. Implementing merge sort involves writing recursive functions for divide sorting and merging the array. Careful attention must be paid in base cases, recursive calls, and merging logic. Programming languages like Python, Java, and C++ have built-in functions for implementing merge sort. Complexity comparison chart. A comparison chart showcasing time complexity and space complexities of merge sort against other sorting algorithms. Visualizing the complexities can help the understand strengths and weaknesses of each algorithm. Merge sort consistent big O of n log n time complexity stands out in the chart. So here is the comparison chart. There are many algorithms mentioned like bubble sort, modified bubble sort, selection sort, insertion sort, heap sort, merge sort, and quick sort. So as you can see, bubble sort and selection sort basically have the time complexity of quadratic time complexity of n square, and so does insertion sort. So these sorting techniques doesn't use divide and conquer as their main strategy technique, whereas heap sort, merge sort, and quick sort to some extent use divide and conquer as one of their design technique. So as you can see here, there is the time complexity of n log n in majority of the cases, which is average, best, and worst. So here, as you can see, merge sort stands out as big O of n log n in all the three cases of complexity. Memory management in merge sort. Managing memory efficiently is crucial in merge sort due to the extra space requirement. Proper memory allocation and reallocation practices can optimize the performance of merge sort. Understanding how merge sort utilizes memory can help improve its efficiency in practical implementations. Parallelizing merge sort. Parallelizing merge sort can further enhance its performance by leveraging multiple processes or cores. Dividing the sorting and merging tasks among different threads can speed up the overall process. Parallelizing merge sort requires careful synchronization to include to ensure correct sorting of the array. Let's see merge sort in data structures. Merge sort in data structures. Merge sort is commonly used in various data structures like linked lists, trees, and graphs. Its stable nature and efficiency makes it suitable choice for sorting elements in data structures. Understanding how merge sort operates can help optimize sorting operations in different data structure implementations. Tips for optimizing merge sort. Optimizing merge sort involves fine-tuning of algorithms implementation for specific use cases. Choose the right base case. Optimizing the merging process and reducing unnecessary memory overhead can improve a merge sort's performance. Profiling and benchmarking merge sort can help identify bottlenecks and areas of optimization. Conclusion. Merge sort is powerful sorting algorithm known for its stability, efficiency, and predictable time complexity. Its divide and conquer strategy, table sorting, and big of n log n time complexity makes it a popular choice in various applications. Understanding the inner workings of merge sort can help developers leverage its strengths and optimize its performance in practical scenarios. We have come to the end of the presentation. Hope you understand the basics and the working nature of merge sort using divide and conquer strategy technique. Thank you.